Hi, so today I want to talk about memoization. So memoization is a concept that if you're doing expensive function calls, you can store the results of those calls, and then when you later need to recalculate those or need to make those calls again for like the same parameters, you can just fetch the stored results and you don't have to recall the function. And this basically saves computational power and saves time. So I'm going to show an example of that with Fibonacci numbers. So here we have them defined over here. The zero Fibonacci number is one, the first one's one. And then after that, you just sum the previous two and so on. So here's the basic Fibonacci code. Um, so it's like similar to what I said earlier. If it's less than the first number, we just return one, else we recursively calculate the previous two numbers. And down here, we have this like kind of call graph for what would happen if we called like fib4. So you can see we call fib3, then 2, and then based on the recursive calling, we kind of go down here, 2, 1, 1, 0, over here, 1, 0. And this kind of forms this like tree-shaped call graph, which ends up being 2 to the n, because each time we increase like the number we're putting in the parameter by 1, so called like fib5, this tree or call graph kind of like grows like deeper and deeper and gets more levels and becomes more expensive. So now let's look at a memoized version of Fibonacci. So first, we're going to use a list to store previously calculated Fibonacci numbers. So that's going to be in prev, and we initialize it to all -1. So basically -1 will indicate whether or not we've stored a Fibonacci number there, since we know all Fibonacci numbers must be positive. And then we're going to use this fib helper to calculate the nth Fibonacci number. So now let's look at fib helper. So we're going to see first we're going to see if the previous in prev, if the nth index of that has -1. And if it is -1, that means we haven't yet calculated the nth Fibonacci number. But if it's not equal to -1, there must be some positive number there. We must have modified it. And that means we previously calculated the nth Fibonacci number, and we can just return that and without any need for more recursive calls, which is like the part that saves, I guess, like computational power and time. And else, if we haven't previously calculated that number, we're going to need to do that. So that's result equals fib. We're going to call fib n-1 with prev and fib n-2 with prev. And then now we're going to update prev because now we've just calculated the nth Fibonacci result or nth Fibonacci number, and we're going to return that. So basically, then this means that for each Fibonacci number, we only need to calculate it once, and every other time that we need it, we can just fetch it from this list. So basically, this memoized version of Fibonacci just becomes ON. So you can see like similar call graph, we do 3, 2, 2, 1, 1, 0. So we basically like the order of recursive calls will just like proceed down this way. So like store 3, 2, 1, and 0. So basically these two calls, we don't need to do anything. And then, yeah, so this is a lot better than this original code we had. We reduced the big O cost by a lot. So you can see like this is why memoization is so useful. Basically, the takeaway is memoization. We can use it to store the result of expensive function calls, and this can save a lot of computational power and improve the performance of whatever you're trying to run.